We got, yes, we're from Owen's like, business, that's me. So I think that's.
Ooh, cutting thorns, that had to be fun. I still think I still think the best one was the branding the cattle.
But other people came up with the point. No one can say this.
I don't know, branding the branding cattle sounded nice. I don't know. You get kicked a few times, you deal with it. What we're doing. Oh, yeah, they'll do that.
They smell or what?
I have a hole about this big.
Cal kicked a hole in the jeans. All right, so we're back to pH. We're going to be looking at the pH of strong acid solutions. So one of the things that sometimes you need it, sometimes you don't, but it can be helpful is knowing what the major species in solution are. Have you guys have latched on to the fact that species means something different? Species in chemistry is more nebulous. It means a chemical species, like for example, in an acid solution, here you have your perchloric acid. And so your perchlorate ion is one of your species in solution. Do I want to know what that was? I heard that. But so strong acids fully dissociate. So you notice how we only have the single arrow here. Full dissociation. So the best way to start to understand this is just to work through a problem. Okay, so solution is prepared by adding 50 milliliters of 0.05 molar. Name these acids, HBr and HI. Close. What's the acid name? Yeah, hydrobromic acid. What about HI? Iodic. Yep, hydroiodic. So remember, these are halide acids. Okay, so we have two chemical equations that are happening here. Are you guys able to do your oxidation states? Because when you're doing homework problems, if I don't get ion charges, that's going to be problematic. Oxidation state is going to be the charge on the ion. Those are your oxidation numbers. Yeah, why? Why is it -1? So you can do it that way. Yeah, there's only one hydrogen on there. So if I take that off, bromide has to be a -1. How else do you know? Yeah, so it's in what, 7A or group 17. Depends, it doesn't matter how you say it. You see it's all the way over on that far right side of the periodic table. And so it's a common charge ion. Okay, so the major species. Major species are components of solutions present in large amounts. They're the primary components of a chemical reaction. And so our major species, let's see, we're going to have H plus, bromide, iodide, what else? What else is in these in large amounts? It's not the neutral molecules. Those are fully dissociated. Those are gone. What else is there? Yeah, water. Okay, so the thing we have to think about is we're adding two acids together. Okay. So what at the end, what we want is we want the concentration that concentration of protons. Okay, so let me give myself a little room so I can write these numbers back in here. But I have so much of a certain molar solution of hydrobromic acid, and I have a certain amount of a 0.1 molar solution of hydroiodic acid. How do you think I get that concentration of protons? Do what? Well, we will once we get there, but we need that concentration of protons. Yeah, and so the first thing we need, how many moles of protons do we have? So let's find out how many moles of hydrobromic acid we have. 0.05 liters. And what? And then how many moles of protons do I get? So this is fully dissociating. So there's no HBr left. It's all going to the right. How many moles of protons do I get from a mole of HBr? Yeah, 1. That is going to end up giving me 2.5 times 10 to the negative third moles of H plus. And again, the way this works, you think of full dissociation. We get 2.5 times 10 to the negative third moles of HBr, and that's going to fully break apart. And so I'm going to get 2.5 times 10 to the negative third moles of each one of those ions. Okay, so same thing with the hydroiodic acid. We will, because we need total moles per liter. This is going to give me 1.5 times 10 to the negative second moles of H plus. Now, both of these are giving off protons. So I need a total amount of protons in solution. That's the total number of moles of protons in solution. And then what is the volume of our solution? Look at the problem again. What's the volume of our solution? 200 milliliters. Over what, 0.2 liters? That's going to give 0.088 molar solution in our protons. So then from here, so our pH is about 1.06. Okay, so strong acids, pretty straightforward. What about weak acids? No, they don't fully dissociate. So let's see, you're going to list major species in solution. If you need to. Choose the species that produce, which species is going to dominate the production of protons. So it's like if you have an acid with a Ka of the order of like 10 to the negative second, and you say, well, water also produces protons, but its Kw is 10 to the negative 14, 10 to the negative 14th. Well, the acid is going to be the dominant source, so you don't have to worry about the water. Let's see, write equilibrium expressions for the dominant species and perform isotable calculations. Use your equilibrium concentration of protons to find your pH. Okay. So here's a fun name for you, monochloroacetic acid. So if you look at that, the way to get monochloroacetic acid, so you remember you have a methyl group. Attached to a hydroxyl group. To get monochloroacetic acid, you have to break up. So this is just acetic acid. You have to break off a hydrogen and put a chlorine on there. Where will that happen? Nope, not. So it can't be on the carboxyl group or else it won't be an acid anymore. So your chlorine is going to have to break one of these and replace there. Yeah, it could be either. It could be any of them. So remember, it can't be that hydrogen on the carboxyl group because that's your acidic proton. So that's why we have our compounds like monochloromethane. So that's your CH3Cl. Okay, so this is a skin irritant that's used in chemical peels, which is always funny. People are like, I'm going to be beautiful, I'm getting a chemical peel. They're spreading chemicals on your skin and then they're peeling your skin off like a glove. So sounds a little rough. So for monochloroacetic acid, the Ka is 1.35 times 10 to the negative third. Calculate the pH of a 0.1 molar solution of this acid. Okay. And so again, if we compared the Ka of this to water, you see the Ka of the acid is much larger than 1.0 times 10 to the negative 14th. So the dominant species is going to be the monochloroacetic acid. Okay. You could write down your major species in solution. That's going to be your, so this one's a little different. You're still going to have because it doesn't fully dissociate, so you still have a fair amount of that left in solution. Let's see. So those would be your major species. And then the reaction you're going to build an ice table out of this one, you have to kind of say, well, it's just one proton that breaks off. So then the anion has to be a negative. And so then your initial values, 0.10 molar, none of that, none of that. Well, that automatically tells us which way the reaction is going to go. So your change plus and plus. Then your equivalent, your equilibrium values. And again, you know, you look at the coefficients of the equilibrium equation, they're all ones, so that's why you have a 1 in front of each x. Okay, so now you need the Ka value, the Ka expression. Notice also that this Ka is on the order of 10 to the negative third. This is about your crossover point of when you can make your assumption versus when you can't. You're going to see one where it doesn't work. You're going to see one where it does work. So if you're still at 10 to the negative third and you don't want to spend your time doing a bunch of 5% rule tests, just do the full method with like the quadratic formula, all that stuff, until you get to 10 to the negative fourth. Once you get to 10 to the negative fourth, you're pretty safe. So the Ka is that. And we look here, that's going to be x times x over 0.10 minus x. And that is going to be our 1.35 times 10 to the negative third. Just for fun, let's see if the assumption works. So that we're going to assume that 0.1 minus x is still essentially just going to be 0.1. And so we could say, well, x squared over 0.1. When I solve for x, it's going to give me 0.0116. Okay, now, the 5% rule is you take your change divided by your initial value times 100. So our change is 0.0116, our x. Our initial value is 0.1 times 100. We get 11.6%. This fails. So again, when you're at 10 to the negative third, if you want to save some time, just go ahead and set it up for the quadratic formula, because some of them will work, some won't, but you're going to have to do the 5% test every single time if you're not sure. So since we know that, this is a no. Okay, so sadly, we have to set it up for the the quadratic formula. Okay. Yep, 10 to the negative fourth. All right, and then we move everything to the left side. All right. Our quadratic formula. So everything's gonna get plugged into there. Okay, the way this is gonna look. So you go through this calculation, you do it both times. One of the values will be a negative value, and that's going to give you negative concentrations at equilibrium, which doesn't make sense. So the only value it can be okay. So we look back at our ice table, and we notice that our equilibrium concentration of protons is just our X value. Okay, and then from here, our pH. And that's going to be about 1.96. Okay, so this was a single weak acid. What about a mixture of weak acids? When you have a mixture, you need to, what you'll end up looking at is you're going to be looking at the proton concentrations from each acid. You need a total amount. Sometimes the dissociation of other acids is so small that the dissociation of just one of the acids is all you need. But you always want to make sure. So here we have a solution, a mixture of 0.5 molar HA, 0.2 molar HB, and 0.1 molar HC. Now, look how much larger the Ka of HA is than the others. We can already kind of see that the others are not going to contribute to the concentration of protons in any important way, but we want to find out. If they do contribute, how many ice tables will you have to do? 3. And then you'll have to add together the protons of all of them. Yeah. Yeah, and I'll show you that. We're gonna do 2 ice tables and see that the subsequent acids are not going to contribute, because if 10 to the negative 10th doesn't contribute, 10 to the negative 12th definitely won't. Okay, so our dominant source of protons is going to be acid HA. So our dissociation okay, my initial values 0.5, 0 and 0. My change and my equilibrium values. Once again, we have a K value on the order of 10 to the negative third. So we're right on that boundary. And this is so you saw the last time it failed the 5% test. This time it's going to pass. So you're going to see why it's ambiguous at that scale. And so I go back to, if you don't want to do the 5% test every time, just assume a quadratic formula for 10 to the negative third. You can do quadratic formula for all of them and get the right answer. It's just, when can you use the assumption? Okay, so let's look at our Ka value. Okay, it's going to be, so our assumption is this is going to equal about x squared over 0.5, because we're going to assume that minus x is not going to decrease the concentration of our original acid in any real noticeable way. All right. It's what? 1.0 to the negative third. X squared is going to be 5.0 to the negative fourth. Square root both sides, x is going to be 0.0224. Okay, now let's do our 5% test. Again, we're going to take our change divided by our original value times 100. So yeah, your change divided by your original value times 100. And it needs to be less than or equal to 5% for the assumption to hold. This is going to give us 4.5%. So you see, this time it passes, but we're still pretty close. So again, this area of 10 to the negative third is one of those really ambiguous areas. Anything larger than that, definitely you want to do the full quadratic formula. At 10 to the negative third, I would just go ahead and do it to save some time. We're going to go ahead with the assumption here since it passes the 5% rule. Okay, so that means at equilibrium, okay, so I now have protons from that first acid. Let's look at now let's go through the process for HB and see how many protons it's going to give us. Could we just go ahead and figure out the pH from this, or do we need all three ice tables and add them all together? Now, if they all had Kas on the same order of magnitude, yeah, you need all three ice tables, add together all the concentrations. But you notice our next two are 10 to the negative 10th and 10 to the negative 12th. Those might not contribute. Let's find out. Okay, so our ice table for HB. Okay, our initial values this time, 0.2. Nothing and nothing. Our change. And our equilibrium values. We're not even, and on this one, we're not even going to do the 5% test. It's Ka is 10 to the negative 10th. We already know for a fact that this is going to work, that we can make our assumption here. Okay, so our Ka value. Okay. So that's going to be x squared over 0.20. And that's going to equal 1.0, 10 to the negative 10th. Multiply through by the 0.2. And then square root both sides to get an x of 4.47 times 10 to the negative 10th. And that's, so the concentration of protons from acid HB is going to be that. Now, the question is, how much did that change our overall concentration? And that's going to give us 0.0224047. So you notice that it doesn't change it at all. A very, very tiny bit. So you can guarantee that the acid HC is going to yield even less. So at the very end, our overall concentration is still essentially going to be 0.0224 molar. Great. We use that to figure out our pH. Now, let's see, did it ask for pH? Oh, no, just calculate the protons there. So you would use that to calculate pH. You could go ahead and do the third ice table, add all three of them together. You're going to notice that HC is going to contribute even less than HB. Now, if you were doing this with three acids that had very similar equilibrium constants, you're going to need to do all three ice tables and then add together all of your proton concentrations. So that's I think that's what's the next thing, percent dissociation. So of course, we kind of want to know when we have a weak acid or a weak base in solution, how much did this acid or base dissociate? Okay, so you have your amount dissociated in moles per liter divided by your initial concentration in moles per liter times 100. All right. And a little factoid to remember is percent dissociation increases as an acid becomes more dilute. What does that mean? More water is going to dissociate more. Okay, so what is the percent dissociation? And that goes back to what that Le Chatelier's principle. So you put the water in, you're unbalancing the reactants, so it has to shift to the right. What is the percent dissociation of 0.7 molar HOBr? Okay. Well, let's look at our dissociation equation. What's my anion going to be? OBr. What's its charge? Do what? What's its charge going to be? Yep. So we say, what's our initial value? 0.70 molar. Nothing and nothing. Our changes. What are the changes going to be? Equilibrium. So let's look at our expression for Ka. Okay, so that's going to be X times X over 0.7 minus X. Can we go ahead and use our assumption here? And why is that? Very, very tiny K value. Okay. So that's going to give us X squared over 0.70, and that's going to equal our 2.0 times 10 to the negative 9th. Multiply through by 0.7. Square root both sides. Compare this to the ice table, and you notice that our equilibrium concentration of protons, nope, this wasn't, we need pH, we'll do that, but we're looking for percent dissociation. So let's remind ourselves of what that is. Amount dissociated over initial concentration. So we have our amount dissociated. What was our initial amount? 0.7. This is going to be 5.3 times 10 to the negative third percent dissociated. Now that's percent dissociation going forward. What about going backwards? You have a 1.0 times 10 to the negative second molar solution of cyanic acid. 17% dissociated. Calculate the Ka for the cyanic acid. Okay. Well, let's start with our ice table. Okay. Initial value. Change. Equilibrium values. Mhm. Okay, so then we say our Ka so we have that. Now I need to figure out what X is. Because remember, this is 17% dissociated. So that's 0.17 equals our change over our initial value. Gonna multiply through and get an X 0.0017. I'm gonna plug that into my Ka value. 0.010 minus our Ka is 3.5 times 10 to the negative fourth. Does this second step here where we started with the 0.17, does that make sense? Because again, you take your 17%, divide by 100, then you have your change over your initial value. Your change is your X. Right there. Okay, I guess we'll pick it back up on Wednesday.